So we start the lecture now. So we are in the middle of providing some algorithm to solve the problem of shortest path, and we study in detail the DISCRETE algorithm. Then we move on with the second one. I introduce the Bellman-4 algorithm. So you may ask, what is the major difference between the two algorithms? So the idea depending on the update equation and the way we choose the vertex or the edges to append to the optimal set of vertices. So I want to go to the slide where I compare the major difference between the DISCRETE and the Bellman-4. Okay. So both of the algorithm update the label by calculating, the length from the path from the root to that current vertex. So only one equation. Actually, equation number one, you remember, and you look to the update equation and you see, well, it's almost the same. But actually, this is not the same. Okay, so this is the idea. You can read this slide very carefully. So in the first paragraph here, up here, you update the label, okay, by computing by comparing the minimum of the old value and the new length from the newly found path. Okay, this is the idea we summarize in equation number one. And the difference is from here, where in DISCRETE you have to update only the vertices which is adjacent to the optimal node inside the capital S, the set of optimal nodes. On the other hand, for the Bellman-4, we don't care that. Okay, we can apply for any edge inside the graph up to that moment. So the Bellman-4 find one to all shortest path, and then can be applied for a bigger class of input, allow you to check the negative cycle. If some negative cycle exists on the way, then the algorithm will stop. So you look carefully into the equation where we express in the internal part here. I mean iteration step here. After the initialization step, you have the label for every node in the graph, including the short node A. Then in the iteration step, you go for any vertex, you see. I mean, the idea in the Bellman-4 look similar than in DISCRETE. Then for any, vertex V like this one, you compute the length from the root to that knot right here. And if the knot U and the knot V is not, you know, adjacent, they are not neighbor in that step, then you know the weight will be infinity. Therefore, the left hand side is never small. So that means we keep the label, you see. But if actually V and U already connected together, then hopefully that the sum of the current label up to the knot U plus the weight from U to V, if this sum smaller than the current label of V, then you must update the label of knot V by replacing the current label by the new length of the new path here, you see. So the idea looks simple, and the number of steps also smaller. Okay, so on the way we do that, then actually this is two loops. If in some instances you discover that the update length to give you the new weight, the weight of the path from the root A to the knot V turn out to be smaller. I mean, after you finish the internal part here, and then you check this one, and if you discover that one, then that means the circuit here has negative weight. Today we will move on to the next algorithm, which run very well for the dense graph. I mean, the DISCRETE and 4 is good, but not much connection inside the graph. For a graph with a lot of edges, then they run slow. Okay, so we will see the Ploy washoe right now, and to see the idea of the Ploy washoe. The idea of the Ploy washoe is not the same. I mean, fundamentally different from the DISCRETE and the 4, where we rely on the concept we call the triangle inequality. Okay, so I skip the illustration of the 4 because the solution very clear on the step by step here. You can run yourself at home step by step and see the way we update the label of the vertices. Okay, so I don't explain this example. Okay, we did that last time, and I asked you to practice yourself, including the backtracking procedure. Backtracking means you can choose any intermediate vertice and you track back to the source. Okay, to track back to the source, we call the backtracking procedure. So if we go from A to D by some path, then the backtrack will return you the path from the sink D back to the source A. So when you learn elementary math in high school, you know triangle, the concept of triangle, and the idea of solving some optimization by using triangle is very popular in mathematics, therefore also popular in computer science. So we get the same input before a weighted graph with n vertices and many edges. Okay, so we are moving to the Floyd washoe. So be patient. We are at the exercise 1, 2, 3, 4 designed for the DISCRETE and Berman 4, and 6 exercise actually. Yes. So last time I promised we continue the story from here. I a little bit delayed the process because I hope that there are, to wait for few students if they come late. So right now today I count here and the number of students is not full. So this is not good, because if the lecturer in our department, in our faculty, I mean computer science and engineering, they give the final examination with many problem regarding the diagram level 4 and something like that, then if you miss the idea, then maybe you cannot find the right solution. You may fail. So try not miss any lecture. That's why we say. Okay, now the new one is from here. Bloy and Washoe are two mathematicians, and we follow their original ideas in 1962. The objectives are the same. The objectives are the same. We want to find the length of the shortest path. We say the distance. In computing, distance usually defined to be the length of the shortest path. So you are given a connected graph, and you choose any pair of vertices, and the graph also weighted. That means we give the weight, usually positive number, to the connection among the vertices. Okay, the graph also assumed to be simple so that you don't have the loop and you don't have multiple edges. Then the Floyd-Warshall algorithm find out the distance, okay, the length of the shortest path between any pair of vertices. The goodness of this, one of the advantages of the algorithm here, is allow you to have the both positive and negative weight. Interesting. But no negative cycle again. Somehow the property negative cycle is not attractive to computer scientists. So we allow negative weight, but we do not allow a negative cycle. And the second advantages of the Floyd-Warshall will be applicable for dense graph. In computing, dense means the graph have many edges. For contradiction, the concept sparse means less number of edges. So given the same n to be the number of vertices, then for the dense graph you should use the Floyd-Warshall, and for the sparse graph you should try the DISCRETE or the level 4. Now we go to the idea we call triangle operation, okay, based on triangle. Imagine if I choose the pair of vertices, let's say any node k, any from the graph, and you choose somewhere else another node we denote by I, okay, and you want to find out a path connecting them together, and several ways to connect, maybe via one intermediate, or can also go in via many other vertices as well. So imagine if you go the intermediate one, like here I denote by J, okay, J here. So we allow the index k and I going from 1 to n, small n, you see, where small n always defined to be the total number of vertices. So any choice of k and I, then you allow the third index j now also going from 1 to n, that means arbitrarily chosen among the total n vertices. Then you can update the length or the distance between, let me see here, Oh, okay. So I have to change a little my announcement here because yeah, I understand. So actually, we consider the intermediate node will be the out loop, the outside loop. Ah, interesting. So by the code right here, actually we have to say that the internal loop is more important. Ah, so I have to redraw the triangle for you to understand the idea. Okay. So there are three nodes. The first choice will be I and J. Somehow at beginning the path or the distance between I and J is denoted to be infinity, and we don't know. So that means there was initialization step where you give the length from I to J, and we did not bypass I and J here. Actually, this one is the distance between I and J. Okay, and then the outlook K here will be the intermediate node. So if we can travel from I to J via not K, uh, so in the triangle here you can draw the connection like this. Okay, from I to K and then from K to J. Then if there exists connection from I to K, then you can get this information from the assumption or from the input of the algorithm, namely the weight. Okay, I and K connect, the distance from I to K exists. Then also K and J connected as well, so the second number here also exists. Then you can take the sum, you see. So I did not, let's say the length from I to K will be A small, and this one will be B. So that means for any choice of K, I, and J, you already finished calculating this sum. Then you compare with the original length from I to J before this step. Okay. If I and J not yet connected before, then obviously this part will be infinity. Then the minimum will actually give you the value of the sum A and B. You see that? A plus B here. But if I and J are already connected and the weight between I and J smaller than A plus B, then you don't change, because the path, the length from I to J is smaller than the sum. Then minimum operation here will keep the length from I to J. So we update, and actually does not change at all. So we already traverse the node K, and we don't change the value from I to J. But if A plus B is smaller than the length from I to J, then obviously the new label will go to the left hand side here, you see. So basically the idea is just conducting comparison between the red connection here with the blue A and B, and after one step you get a new one path I to J, mean the distance from I to J, perhaps get a minimum or better a smaller value, and that's all. Okay. So therefore you can prove mathematically that for any weighted graph, the problem to find out the shortest path from any pair, any vertices to vertices, we can on to on. Remember, in the first day we define that one. This one gives you the algorithm with complexity O, big O here, and the cardinality of V will be n, and you see this one depending only on the number of vertices. That's why the Floyd Washoe run very well for dense graph, because the complexity just depending on the number of vertices, not depending on the number of edges. Okay, so we can see details of the algorithm via example number 1, where I give you the graph here to have in total 4 vertices. And by the idea similar to DISCRETE and Bellman-Ford, we denote the distance matrix. I apply LM here to be the distance matrix. This one is the square matrix upside n, of course. In this case, n to be number 4, so this one have side 4 by 4. And the upper index m here tell you the value, the maximum M connection. Okay, so that means when you give M to be 0 like the first instance here, that means you does not yet incorporate any arc, any connection between a pair of vertices. You understand, right? Actually, you can write more information here by assign, by label the row A, B, C, D for the row, and the distance matrix is similar like the adjacency matrix. Remember, that means you have to also label the column by A, B, C, D as well. That means the column again we use the notation A, B, C, D, the row A, B, C, D, and the column as well. Then let's take a particular connection and see. We start from A. You go to A, of course, distance to be 0 here. Do not change everything. Can we connect directly A to C? The answer is not, because this is a directed graph, and you see we can only go from C to A. Therefore, from A to C, we don't have the arch. Okay, that's why this one to be infinity. This is one way. You can say one way route from C to A. Yes, C to A. Actually, you can read from the third row here. Third row here, C to A, and the value of the width of the one-way route from C to A is number 3, and I put number 3 here in the first column, the third position. You see, so that's very clear. But from A to C must be infinity, and from A to D from the graph you see number 4, and I brought here. So that means in the matrix L we put small m to be the upper strip, but inside the matrix we put value m to be the subscript here 0. That means m. We don't put up, so that is the way to distinguish them. So let's see, well, randomly chosen from D to B, let's say D to B. That means the last row and the second column, and you see -5. D to B, yes, this one -5. You see, so basically the matrix L0 very trivial. You can copy information on the graph from the left, and you fill in with the new way, new convention, that if there is no root, then you put the infinity. Okay, and then don't forget the subscript to mention that we are in the initialize step. We just copy. Actually, L0 can be considered to be the weighted, the adjacent graph, but we put the weight inside. Okay, now everything become more interesting if we continue the iteration. Now we move from 0 to using one arc. Okay, m to be number 1. All right. So I illustrate the idea very slowly for one case, and because after that you have to understand, and you carry out similarly for many exercises yourself. Okay, we don't have time to solve all. We have time to illustrate only one case. Now m to be number 1. Yes, So from A to B, C, D, and not change because actually one arc. So that means from A to B we employ this connection, and the number one is right here for sure because the first row is A, the column will be B. So B will be the second one here, C will be the third one, etc. Now look to the second row. Okay. Right now I copy the first column, but I not yet fill in the entry inside, you see. So let's talk about from B to B, second row, second column. Can we go like that from B to B? Well, interesting because this is directed trap. Go very slowly. Right now we can go from B to A, right to the left, and then we go back from A to B, left to the right. That means if you consider a path with two arcs, then exist from B to B. But if you consider a path with one arc from B to B, not exist, right? So BA and AB, that's two arcs. Right now, the upper strip here, number one, that means not yet two arcs. So not yet, don't hurry to fill in that, not yet. That's why this one still be number 0, you see? You have to go very slowly. Now about from B to C, that means the third column, yes, B to C minus 2 already there. So basically I will keep the black color if I don't change, but I will update by the blue if there is something change. You follow me? So now from B to D, the second row and the last column. At the beginning, from B to D, B to D, can we go 0? No, but can we go from in the second trap, second matrix here, why number 6 appear and number 1 here tell you that you can travel? I wonder why. The blue, the first blue in the second row, number 6. Why is that? I'm wondering. Okay. Then actually you can go from B to D, but with two connection, actually it will be BAD, and then the weight will be 2 plus 4, you get number 6. So actually right now the blue mean hopefully, okay, we not yet apply the red. When you apply some number by red color, that means you employ M arc. So right now the left hand side you see we employ only one arc. So this is the prediction. Number 6 with the blue means we predict that will be the value in the second step, the next step. Okay, by the same idea, let's say about the number 7 from C to D as well, the third row, C right here, cannot go directly to D, but we can go via the node A, you see. CAD will give you number 7. So by the same idea, the color will have very meaningful role in your algorithm if you want to understand. So that means not yet turn red, that means just hopefully in the next step. And the answer is yes. We see in the M to be number 1, now you see M to be number 2. Now fully number 6 become red. This is illegal now, become valid now. Okay. Number 6, you can go from B to D by 2 connection. Number 2 by here, you see? And with the width, the length or distance will be number 6. And this go like this one, okay? B go back to A, we call this the arrow. And then from A go right here to D, you see? And the sum will be number 6, exactly. So by this way, you can extend the distance matrix LM step by step by looking to the left of the graph and continue that way. In step number 1 here, there are 3 blue number, 6, 7, and 4. Then they turn number 6 here, they turn number 4 here. But why? Can you wonder why number 7 here still black one? I am curious again. So this one is the row C and the column D. So why number 7 not change from blue to the red? Line number 6. You see, C to D, C to D, C, A, D, 7. So there are some reason. We not yet know why, but well, but in the matrix L2, right left corner here, before that it was infinity. That means from D to A, infinity by 1 arc. No way to connect D to A. Yes, because from D you see here there is no direct connection, one-way route from D to A, so infinity correct. But L2, this one turned out the blue -3, and now you understand, right? Because we hope we can travel by 2 arcs. And why number -3 in the leftmost entry here, left bottom, -3, blue one from D to A? Yes, because the first column in A, D to A, and you see we can go via not B, you see, and -5, and you get +2, and you get -3. That means you get one route, one way, DBA. And you may ask me why not going from, guys, tell me the second route from D to A, except the DBA already. We see that. DCA, yes, correct, and the weight will be number 2. And because you see the minimum distance, so you compare number 2 and number -3, and you have to choose -3. Now you understand why and why, okay? So there are 2 routes, one-way route, DBA and DCA, but the one DBA better because it's you smaller weight. Okay, now the blue is there, 5, and by the same idea you can update the 7, -7 inside here from D to C by 2 connection. Really? Why -7? Because before that you get number 0. Well, yeah, you can go up again, DBC, right? DBC give you number -7, the root DBC, you see. And actually before that, from D to C you get -1, direct connection here, yeah. But the new root give you smaller value because -7 smaller than -1, right? So that's why the blue appear right here in this position. So very interesting. I mean the idea, triangle optimization is simple, so simple. But we apply, and you see the computer will run very fast. Okay, if you have the code and run 1 second, then but we have to understand. So that's why I go slowly. Okay. M to be number 3. We continue, and the number 7 here now turn red. So maybe the mistake somewhere. Actually, it should be turned red before, but now we confirm from C to D, number 7 from C to D. This is the root CAD. Yes, exactly 2. But the matrix now L3, so that means we say 3 connection. Actually, if the number of connection is bigger than 2 but does not change, so that means we keep the previous value by the algorithm, right? We compare again and does not change. 3 plus 4 will be number 7 at this corner. Moreover, the blue minus 7 here now also turn red. That means already minimum. Remember, Wang and Wang got thought that maybe not optimal, but now the blue turn red. That means already optimal. The route from D to C via D to C will not be, yeah, DBC, the route DBC, okay? And you have to update, I mean every step the algorithm will update the value inside the distance matrix. And very interesting, like if you compare the new matrix from here, this is the new matrix, okay, with the previous matrix, and you discover something changed, right? For instance, very interesting, I would like to say interesting phenomenon here, which is number 6. Yes, this is from B to D. If you employ 2 arcs from B to D, and this one tell you number 6, from B to D, 2 arcs. Why? Because you go BAD, right? And BAD gives you number 6. But now, why we get number blue? The 5, number 5 blue, with color blue. Why we go from number 6 down to number 5? Can you explain me via the chat box? In the matrix L3, from B to D, yeah, from B to D before we get number 6, so now we get number 5 only. Interesting. Someone tell me, so Vin and Wang answer BCAD, so let me check. Well, BCAD, that means you employ 3 arcs, okay? BCAD, yeah, BCAD. And the sum of that give you exactly number 5, is that correct? BCAD? Yes, correct. So you see, so the algorithm change every step. The more are involved, then hopefully the label of the distance between the pair, not to see, can be updated, could be updated. Okay, so very clear from the last instance I explained to you, number 6 down to number 5, but not yet confirmed. That's why we write the blue, right? So Vin and Wang, okay, keep that. You get 1 bonus later, okay? And I explained this is enough, so you should track down yourself the other cases. I don't explain more because I show you all of the interesting cases, okay? Now move to L4. L4 will be the last. So if you compare the last column here, you see 4, 5, 7, 0, and all of them now turn out to be red, 4, 5, 7, 0. But the internal part are not yet. Okay, you should do yourself at home later by the same idea, because I explained carefully from 0 up to 3 arcs. And the algorithm not yet stop. And you may ask very crucial question right now, that when will the algorithm stop? Will it run forever? Okay, and the guessing will be no, it cannot go run forever. It will stop at somewhere. But what is the stopping condition? So maybe the first guess will be say, well, That is where at some step M in the future, then the matrix L. This is my guessing. I don't know. We will see later. Okay, because this is the way we design algorithm and the stopping condition. There are several ways to define, but for this strict problem, we hope that the algorithm will stop at some point in the future where the LM plus 1, the distance matrix equal to the LM. And then that means they're not change after one more step and we have to stop. Okay, this is easiest way to look at. And now we get number 4, D. But there are still some blue inside. Interesting. From C to B with the weight number 2. C to B. C is here. To B is there in 4 arcs. And the weight is number 2. So only one way from C we go up A, 5. Then where can we go? Maybe we go to B, only 2 arcs. And then you go where? You go to A again. That means 3 arcs. And you go back to B again, 4 arcs. Maybe you have to check. Why? Why number 2 blue here? Interesting, you see? It can be updated from the previous, but the previous it was number 4. Okay, and you see the new phenomenon happening here when you go from L3 to L4. That from C to B, the label already red already. Okay, and now update to smaller value, it turned out to be number 2, you see. So interesting. Some value turn red, now turn blue again. Okay, 3 arc number 4, 4 arc number 2. So why? And Hậu Quang say I should follow CADB. Wow, 4 arcs. Actually 3 arcs. CADB, that means 3 arcs. CADB give you -2. Yes. CADB, correct. +2, sorry, +2 because 7 minus 5. CABD actually 3 arcs. So we not yet turn red now. That means we expect to see the matrix L5 by the same idea before. Some red turn blue and then the blue must turn red again. Otherwise we cannot stop the algorithm. I mean the Bloy Marshall to me is more interesting than the Bellman 4, I think. Okay, then let's see L5. This one not yet finished. Yes. L4, then L5, not yet show you, not yet. But computing L4 inside matrix L4 from B to D, that means second row and the right hand side here. And before it blue, now it turned red. So equivalent to check the other part. So I will focus on the distance from B to D. B to D before here blue, after that red, but does not change. So we are computing from B to D, and this is my explanation. Okay, BC plus CD. Yeah, BC plus CD. From B to D. So actually this is minus. No. BC 5. But CD exists? No. We do not use the -1. Be careful. The CD you have to read from the matrix. The matrix here, which is number 7. Be careful because this is a directed draft. You have to employ the value from the previous. This is the matrix You cannot read number from original draft. Very careful. Okay. So this now you understand, because you go from B to C minus 2, but from C to D it costs you 7. Yeah, 7 here, right here. Okay. So that means you get number 5. So this is my explanation, very explicitly there inside the graph. Now you continue the same story to explain for this entry, but I don't explain. Sometimes you employ L3, sometimes you employ L1. So depending on the pair vertices. The 7 at the corner right here, very interesting, because you have to decompose exactly by 3 connection. Okay, and that formation you read from the matrix L1. Okay, BC minus to CA plus 3, and then AD plus 4, something like that. I mean, we do by hand, but when you write the algorithm correctly, then it runs in a bit of a few moments. And the second example, I give smaller size. You have here only 3 vertices, but still directed, and the size of the distance matrix is smaller, and you should try it yourself. Okay, you should try it yourself. There are a few cases to look at, but this one differs from example number 1, because this is the first time you say that some number turn red and we get negative number. So this is the major difference between this and the previous step, the previous example. The previous example, you see the distance matrix, we don't get negative circuit. Why circuit? Well, let's say a lot of negative number, but they do not make a circuit, right? Because this one means from B to C, not circuit, and this one means from A to C. You see, so the circuit means from a path moving from A to A itself, in general from U to U itself. Circuit means the beginning and the stopping are the same node. So example number 1 does not have circuit with negative, but the last one here, you move from C to C, right? The last row and the last column, and we are talking about this one, and we discover that negative circuit until the matrix L2. Okay, 2 arcs. So you go by C, go to A, and from A you go to B. That means the sum already number 3, and you go back C to make a circuit. And that circuit will give you the sum of the weight will be minus, and that we call negative circuit, or better circuit with negative length, negative distance. Okay. So the employee washer algorithm say we have to stop, because if you run more, then you get infinity loop 1 to 5, but does not allow circuit. A circuit already make this one, and we go back again, and we will go to minus infinity by the same idea. Okay. So this is the way we discover the best instant to stop the algorithm. Now the first exercise, you have 4 vertices, directed trap, weighted trap, and should do yourself. Okay, exercise 2, 4 vertices as well, and also directed draft. And then this is the first real application. Real application. I am thinking this one very interesting, and I hope you can enjoy reading the detail of the assumption here. Then try to, after understanding the assumption models, do the modeling step very carefully, because we don't see any draft here. But actually, this will make you give you very large draft. Aha. Ho Wang, can you turn on your audio and read for me? Wang, I want to hear
Yeah,
your
yeah,
voice. Read
yeah,
the
yeah.
assumption here, right? Read that.
Uh, a young professor in Hue is invited to teach some years in Ho Chi Minh University of Technology. He decided to represent the diverse operation of heat transfer by craft and, in this purpose, establishes the list of following operations.
Good. A.
I buy the house in Ho Chi Minh City. B. Choose remove a man and sign the contract of move.
Thank you. That's
C.
fine. That's
Make
Wang. That's fine. Good. Lovin,
yeah,
continue.
yeah, okay.
Lovin, continue. Not
Yeah,
C.
thanks.
Yeah. When Lovin.
Can you hear me?
C. Yes, I hear.
Uh, make package furniture by the removal man. They make transport his furniture towards Ho Chi Minh City. He find an accommodation to Ho Chi Minh City from Huế.
Hmm.
F. Transport his family to Ho Chi Minh City.
Okay.
G.
That's fine. That's fine. Vin. Okay. Vicwa, continue the story from G, not G. Where is Vicwa? Next, not G. Read that, please. I would like to hear your voice. Where is Wa? Not hear you, not yet. Wa. Oh, not here, not here. Okay, thank you. Now, Win. Can Win read for me this one? Win, thank you. Thank Wa. Next student, can help me with that. I see that today Win. Sorry, Win. Yeah, U E A N. Yeah, with you. Yes. So, Nguyễn Thị Phương Nguyên.
Okay, I will continue. Number J is fit out the new accommodation. You mean the number J?
J.
Uh,
F after F after not F.
okay. Move into his new accommodation, and H is register the children to the new school. I is look for the a temporary work for his life. J is fit out a new accommodation and pays the arrangement with new treatment of his wife. The last one is find a small bar to celebrate in family the success of the move and express the enjoyment to live in a good accommodation arrangement.
Thank you very much. So, imagine that you do modeling for practical problem like that in the future when you become engineer and you see that the number of vertices can be large. Okay, you see you have 4 nodes, you have 8 nodes, and then 3 more. That means in total you have 11. So the graph is large enough to study with the number here 11 vertices. But we don't see the question now. We also know the very general requirement. He want to design, represent this one so that he can establish new life in the community to teach some here. Therefore, we need to see more things. This is not new information. So that mean this one would be enough. So actually the problem number 1 here is somehow the requirement not so complicated, because you want to draw the draft and you say the outcome will be undirected draft or directed draft, and that's all because we don't see the weight, we don't ask some optimal bath, something like that, see. But don't worry, we see the next one. The first one is just the warming up exercise. In the second one, we try to push application one to a higher level of difficulty. Okay. Now for some node, you define the ordering. We call the ordering constraint. So if you think A to be some activity, in this case will be one node, and F another activity, and when you write A is smaller than F, you mean you have to conduct, you have to perform action A before you can conduct action F, and the same idea for the other pair. Okay, and you have to draw the directed draft following that convention. So in terms of draft theory, that means you denote the action by some node like this one, and you say because A must be done before F, therefore you must draw a connection like this, and you put an arrow on that connection, you see. So that means if you draw every instance like this, then you get the directed draft. Moreover, there are some special case like this one. So let's say C smaller than D and F. So that means this one becomes C and D, F together. So how can you interpret the meaning of D and F? This is the problem. So we understand the idea of smaller, but now we have to interpret the idea of D and F. So shall we draw something like this? That means you conduct C first, and after that you can do the action F as well. So if that is the case, then how do we say about D and F? You have some idea to tell me, right? So C to D, that's fine. Similar C to F, that's fine. So after you got the job C done, you can do D and F. But because you have to understand that after this you have something else, same idea right here, you see. The F must be done before G and H and G and H and I, yes. Moreover, you have also provided some number here. We call the processing time. That means you need to spend 10 hours to finish job A, 2 hours to finish job B, etc. So you need time to finish one action, and the time to finish on of each num is provided in this table. The final one is K, so A, B, C, D for E, F, G, H for this is exactly 11 nodes we define in application 1. So now you know how to match the problem 1 and 2 together, you see. So for instance, the node K here will tell us that about finding small bar to celebrate the family of the successful move, etc. And the job K, action K, need 2 hours. That would be fine in reality, you see, 2 hours. So somehow problem 2 require knowledge of problem 1. You have to continue from problem 1. And you draw the draft, and you see what are the meaning of the and operator right here. Okay, then after that you see the real problem here, the question. You have to determine the schedule of the movement so that you get the minimal duration. And the idea of minimal duration means the path with minimum length. Haha. So now you see the meaning of the algorithm we study. Minimum duration to finish on of the job in this list means to find out a path with minimum distance from the source A to the sink K. K meaning the final day where you enjoy the celebration. Okay. Then the next question will be, what happens if that new accommodation of the professor is not available before the date? Okay, so this will be a critical question. You have to think more, and you have to modify something, maybe modify your draft, etc. So that considered the first real application of scheduling problem employ the algorithm for shortcut path. And that leads us to the question here, more general question. How can we determine a shortcut path from U to V in a draft sheet which travel at most a given constant? So this is a new requirement. You not only to find out a minimum distance path, but also the minimum distance path should get not bigger length, not bigger width, not bigger some constant. Okay. Given constant number of intermediate. So this one is not about the number for the width, but this is the number of intermediate vertices. That means you don't need to use all of the vertices inside the graph. I mean, when you travel from U to V, if we don't have the equation, then you can find a connection where you can use a lot of intermediate vertices. But by this one, if I give you only 4 intermediate on the way, then we do not allow the path with more than 4. You see what I mean, right? So this already 1, 2, 3, 4. So if I give the constant here to be number 4, then the minimum distance path like this one will not acceptable because you employ 5 nodes already. You see, 1, 2, 3, 4, 5. So that means more constraint on optimization problem. And then you have more extension from that. So this is the reality. This one will be provided in the master program in the future, because for your bachelor degree, second year student understand DISCRETE, Payment for Employee Washoe, and so on some intensity, that will be fine. For this one, we study later, maybe in another courses. Okay, so only the shortcut part, you have some variation here. Then we also allow some extension right here. Right now, you do not understand. Okay, we do not study now. So, I mean, the shortest path problem is very huge topic. So, in the next few slides, we briefly, summarize the idea, but we don't particularly study, right? So, take a break. We have a 10-minute break, and we go back at 4:20. Resume at 4:20. Okay? 10-minute break.